Okay, good afternoon, everyone. Welcome to today's PRISM seminar. I'm Ian Lai from TSU. So today we are very happy to invite Dr. Pekka Janhunen to give a talk. Okay, let me introduce him. Dr. Pekka Janhunen finished his PhD in University of Helsinki in 1994. So now he is a research management in Space and Earth Observation Center in Finnish Meteorological Institute. He is well known as the inventor of the electric solar wind cell, which is a propulsion for a spacecraft. And also, he is an expert of the space plasma, especially the hybrid simulation of the solar wind interaction with the planet. So today he will talk about the Coulomb drag propulsion. Okay, let's welcome him. Yeah, please.
Okay, thank you very much for your introduction and good afternoon, Space Union. That is your name. Okay, so this seminar's topic is Coulomb drag propulsion. So what is Coulomb drag propulsion? So Coulomb drag propulsion means that we charge a tether to a high voltage, that it's the electrostatic field which surrounds the tether acts as a plasma sail, as a virtual obstacle for space plasma flow. And for this to work, we need a natural plasma flow, such as the solar wind or the orbital RAM flow that is encountered by a low Earth orbit satellite, or something like that. We could also imagine using the plasma flows inside giant planet magnetospheres or something like that. So the tether that we need for this technique, it can be very thin because it only has to stay charged. This is the main reason why this method can be is interesting from the commercial and technical point of view, because it results potentially very high intrinsic acceleration. I mean, intrinsic acceleration means the thrust divided by mass of the tether. So when we have the tether in space plasma, it of course collects some current from the plasma, but in our technique, this current collection is a side product, not a goal. And in this way, this method differs fundamentally from the more well-known, perhaps more well-known, so-called electrodynamic tether, which is based on the Lorentz force. Then our method also requires some amount of electric power because we need to maintain the tether charged, but the amount of power that we require is not large. And then our method is independent of the surrounding magnetic field. And this means, it implies, first of all, that this method works in solar wind also, where the magnetic field is quite weak from the propulsion point of view. And when used in low Earth orbit, this has nearly uniform efficiency at all inclinations. And in this way, this also differs from the more well-known electrodynamic tether propulsion. And then this Coulomb drag propulsion works for both positive and negative tether polarity. So the plasma physics is different in each case, and I will discuss both in this presentation a little bit more detail. So the selection of polarity, how do we select whether we use positive or negative polarity? So first of all, the negative polarity method consumes less power than the positive polarity method because the ion current collection is much smaller than electron current collection. This is just due to the higher mobility of electrons, higher thermal speed of electrons in any plasma. But on the other hand, the negative polarity case is limited to about roughly 1 kilovolt potential voltage because of the electron field emission from the surface of thin metal wires of the tether. This is the so-called Fowler-Nordheim emission. That means that when you have a thin wire or tether which is biased at high voltage relative to the surrounding plasma, the electric field is enhanced around the tether, around the wire, because the wire is thin. And if the electric field becomes sufficiently large, then it can directly extract electrons from the metal matrix. And this is not, I mean, this is the same phenomenon that happens in some types of field emission electron cathodes, for example. And this is an unwanted phenomenon in our case, because it would increase the power consumption strongly, because this Fowler-Nordheim emission is such that when it starts, it increases very rapidly if one increases the voltage. It's a very steeply increasing function of the voltage. So therefore, the bottom line is that the negative polarity is limited to about 1 kilovolt for this technical reason. And in the solar wind, the proton kinetic energy is typically in the range 1 to 4 kiloelectron volts. I mean, it's 1 kiloelectron volt in the slow solar wind, and about 4 or even 5 kiloelectron volts in the fast solar wind. And this 1 kilovolt negative tether would deflect ions only weakly, because the tether voltage should be much larger than higher than the voltage of than the kinetic energy of the incoming ions. And therefore, we prefer to use positive polarity in the solar wind, and this is what we call the electric sail or E-sail. But in low Earth orbit, we can use negative polarity, because in the lower orbit, the relative speed between the spacecraft and the plasma is about 7.8 kilometers per second. This is the orbital speed of the satellite. So RAM flow, ionospheric RAM flow. And then the main ion species is oxygen ion, atomic oxygen ion there. And that the kinetic energy of that ion is only about 5 electron volts at this 7.8 kilometer per second speed. And therefore, this 1 kilovolt voltage is much higher than the 5 electron volts, and therefore we can use negative polarity. Positive polarity case, this E-sail case, to maintain the positive polarity of the tether, we need to pump out negative charges from spacecraft system, and for this we need an electron gun. The negative polarity, which we call the plasma brake because it's used for braking in the ionosphere, it needs a high voltage source and an electron gathering surface. We could also use an ion gun, but because ion gun, well, it's more complicated device, and it would also consume propellant. Therefore, we just prefer to use an electron gathering surface. I will talk more about what kind of surface that could be. Okay, so then I now go to discuss the E-sail, so electric solar wind sail, which is the positive polarity case working in the solar wind for generating interplanetary propulsion. And there are two main architectures of these E-sail systems. On the left, we can see the single tether architecture, where we have just one tether which spins, and it has some mass at the end, which we call the remote unit. And the remote unit needs some kind of auxiliary propulsion in order to maintain in order to manage the spin rate and the spin rate and the spin plane of the tether. And on the right hand side we have the multi-tether E-sail composed of many tethers, and there we connect the tips of the main tethers by what we call auxiliary tethers, or aux tethers for short. Then here is a particle in cell simulation of the E-sail. So on the left you can see ions, how ions are. Well, we see ion density around the positively charged tether, which is the white dot in the middle is the positively charged tether, and the ion stream, solar wind, arrives from the left. And then the electron density is seen similarly on the right-hand side. And then what we can see here is that there is a wake or vacuum of both electrons and ions appearing behind the tether on the night side, if we call it night side. And of course, we can see that this picture looks qualitatively similar to Earth's magnetosphere. Although there are, of course, two very important differences. So first of all, this is an electrostatic interaction, not magnetic interaction at all. And the other important difference is that this is a truly two-dimensional system, because the tether is very long and perpendicular to the simulation plane. So this is a truly two-dimensional system. But we would perhaps call this structure which forms an electrosphere in analogy with the magnetosphere. And the dimensions are such that the width of this structure is about the radius of this structure is effectively about 100 meters in this case, with the normal solar with average solar wind parameters at 1 AU distance. So 200 meters diameter, 100 meter radius is the effective sail area around the tether. This 100 meters it's about 10 times the plasma Debye length, and it scales with the Debye length. It's 10 times because the voltage here is about 20 kilovolts, so it's much higher than the kinetic energy of the protons, which is about 1 kiloelectron volt. So this is how the system scales in the solar wind case. There can be, based on the simulation results and then based on some analytical models which are kind of calibrated with the simulations, we can have an approximate thrust formula. This is the thrust per unit length of tether for the solar wind. So this is an approximate formula which is roughly valid for the solar wind case. So it's some numerical coefficient 0.18, and then the voltage of the tether, so it's linearly proportional to the voltage of the tether. We also subtract a term V1, which is the bulk kinetic energy of the incoming solar wind protons or ions. And then the thrust is proportional to the square root of the dynamic pressure of the solar wind. So it's proportional to the square root of the solar wind density ρ and linearly proportional to the solar wind velocity v. And numerically, this is about 500 nanonewtons per meter at average solar wind at 1 AU distance at 20 kilovolt voltage. More accurate formula also exists in one of our papers, but this more accurate formula is not so easy to understand on the screen because it's actually a pair of equations which must be solved using iteration. It's very easy to solve numerically, but one cannot. One has to do it numerically. One cannot It's not a closed form expression. And then one noteworthy thing about this thrust formula is that because this is proportional to the square root of the density, therefore the thrust scales as 1 over distance, 1 divided by distance from the sun, 1 over r, because the solar wind density depends like 1 over r squared, and then we take a square root of that, we get 1 over r. And this is very good because this is very good for outgoing missions in the solar system, because competing propulsion methods have a 1 over r squared dependence for the thrust. So photonic sails, I mean the so-called solar sails, which means photonic sails, they have 1 over r squared dependence because the solar radiation, sunlight, scales as 1 over r squared. And also solar electric propulsion devices, they also have 1 over r squared dependence because they are dependent on the power, and the power scales as 1 over r squared because it scales like the power received by the solar panels scales as 1 over r squared. So what is the power consumption of the E-sail? So to answer that question, we need to predict what is the current collected, what is the electron current collected by the positively charged tether. And there is a well-known theory, so-called OML theory, orbital motion limited theory, for cylindrical Langmuir probes. And this theory gives this expression, which is shown here, for the current per unit length of tether. So it's linearly proportional to the n naught, which is the n0, which is the plasma density. Then it's a square root of the voltage V0. And then there is numerical factor 4.3, which comes from the fact that our tether is made of 4 subwires. And I will come later to the reason why this is so. So we have 4 wires. And then 2 of the wires are crisscrossing also. So their length is a little bit longer than the other wires, and therefore we don't have exactly 4 here, but 4.3 coefficient. And then 2 times RW. RW is the wire, single wire radius. So 2 times RW is the wire diameter. So this current depends on the projective area of the tether. So it's if you look at the tether from any direction, you see the projected area, and it is diameter times the number of wires. And this is about 20 nanoamperes per meter, again in average solar wind at 1 AU distance, and 20 kilovolt voltage. And this corresponds to power consumption of about 0.4 milliwatts per meter of tether. And then if one divides the power consumption by the thrust per unit length, which was on the previous slide, 500 nanonewtons per meter, one obtains the power consumption, specific power consumption, as 800 watts per newton. And this is about 25 times less than, for example, for typical Hall effect thrusters. That means electric propulsion thrusters, which have typically like 20 kilowatts per newton of power consumption. And what is nice here is that the power consumption scales in the same way as the solar panel power. So it's 1 over r squared. So it's not, so although the thrust is 1 over r, the power consumption scales as 1 over r squared. So that our power consumption scales in the same way as the solar panel power if we move outward in the solar system. So we become more and more competitive against other methods when we move farther away from the sun. Okay, so then about the control of the multi-tether e-sail. So how does one actually fly this e-sail? So the thrust magnitude, first of all, is controllable by simply changing the voltage and current of the electron gun. So for example, we can always turn off the e-sail propulsion by just turning off the electron gun. And this is it sounds simple, but it's very beneficial. And so for example, the photonic sails, solar sails, they don't have this property. So once you have opened the sunlight reflecting membrane of a solar sail, you can't hide it anymore. So you will produce this propulsion and you cannot turn it off anymore. But the e-sail you can turn off at any time. And then you can also do thrust vectoring. That means that you can change the direction of the thrust in a limited way. But anyway, you can control it perhaps plus minus 30 degrees in a cone which is centered around the anti-sunboard direction, the direction of the solar wind. So thrust vectoring by turning the spin plane, and this spin plane can be turned by differential voltage modulation of the tethers. The algorithm how to modulate the tethers is something that resembles the algorithm that is used for helicopter flight. And then there is one effect which we call the secular spin rate change. And this is due to the fact that if we are orbiting the sun with our sail inclined relative to the solar wind, let's say the inclination angle is alpha, then because the sail is spinning, the tethers are spinning, the angular momentum conservation means that this spin plane of the sail tends to be constant relative to distant stars. I mean, this is just due to the angular momentum, vector angular momentum conservation. And therefore, if we are orbiting the sun, we have to actively track the sun in the local sky. So we have to actively turn the sail all the time when we are orbiting the sun. And this can be done by the differential voltage modulation, but there is a side effect of this. And the side effect of this is that the spin rate of the sail will change. And it will change more and more as we are orbiting the sun, and this change is actually exponential because it's multiplicative, and this change is exponent of omega, capital omega, which is the angular speed of the Earth, of the orbit of the spacecraft around the sun. So for example, if we are at 1 AU distance, then omega is 2 pi divided by 1 year. And then tangent alpha is the inclination angle of the sail. So if we don't incline the sail at all, so if alpha is 0, which means that our sail is completely perpendicular to the solar wind all the time, then we don't get this secular spin rate change. But then also in that case, we can't produce any thrust along the orbit. So our thrust would be purely radial in that case. And that is not very useful for most missions, because usually in missions we want to spiral inward or outward in the solar system. And that means that we have to generate tangential component of the thrust along or against the orbital velocity. And therefore, this secular spin rate change is an effect that we have to deal with. And in this case, we can overcome this secular spin rate change by modulating the auxiliary tether voltages by using a scheme what we call TI modulation. This TI modulation just means that, I mean, I won't go into details regarding that, but I just say briefly what the letters mean. So it means that every second main tether is connected to both its adjacent aux tethers, so that it forms a T-shaped equipotential region. So main tether and two aux tether segments that are touching it at the remote unit. They form a T-shaped equipotential region, which is controlled, whose voltage can be controlled from the main spacecraft. And then every second, main tether is not connected to the aux tether electrically at all, so that the remote unit is insulating point in that case. And this we call an I-type element, because it resembles the tether I, because it's just a single main tether which forms the equipotential region in that case. And by modulating these T's and I's, all of them around the sail in a certain way, we can control both the spin rate and the spin plane. So we can do thrust vectoring and thrust, we can do thrust vectoring and spin rate control independently from each other. And on top of this, we can always do thrust magnitude control by changing the magnitude of the voltage and current of the electron gun. So we can get basically full control of the system by using this kind of geometry. The only drawback here is that our thrust vectoring is a little bit slow. So because the thrust vectoring requires physical turning of the spin plane, and the spin plane turning by the E-sail effect, it takes some time because the tethers are so long. So it takes maybe 1 or 2 days typically in typical solar wind, of course depending on many parameters, but typically 1 or 2 days to turn significantly the spin plane. So it requires some kind of planning of the orbit in order to take this time delay in thrust vectoring into account. Okay, so that was the multi-tether E-sail. So then what about the single tether E-sail? So the single tether E-sail is for interplanetary CubeSats, so it produces much less thrust than the multi-tether system, obviously. And in this case, the remote unit needs auxiliary propulsion, first of all, to start the spinning, and then also to overcome the secular spin rate change. We can use, however, the differential, not differential, but voltage modulation in synchronization with the spin rate in order to change the spin plane of the device. So we can turn the spin plane by using the E-sail effect alone, but then we have to, then if that results in a change in the spin rate, we have to compensate for that using active propulsion at the remote unit. And one feature of this single tether system is that the main spacecraft can do pointing freely if the tether is attached at its center of mass. And this is a useful feature, so we don't need gimbaling of a telescope, or if we have a scientific instrument such as a telescope, for example, for taking pictures of asteroids, flyby imaging of asteroids, then we don't need a gimbaling for the telescope. We just need reaction wheels in the CubeSat, in the main spacecraft itself. Okay, so let's now go to discuss the tether. What is the Coulomb drag tether? We call it actually micro tether because it is so thin. So our tether is made of 4 wires. We use so-called Hoy tether geometry, which has 2 parallel wires and then 2 crossing wires at the middle. And this strange geometry is selected in order to be micrometeoroid resistant. So because there are micrometeoroids in space everywhere, we cannot use a single wire as a tether, because if we use a single wire, it will be cut at some point by a micrometeoroid hitting it. And the predicted lifetime of a single wire which is 20 kilometers long, for example, is too short. And therefore we have to increase the lifetime by making the tether redundant. And this tether width is for the e-sail is 1.5 centimeters. And here we see a tether on its reel. This is a 60-meter piece of tether reeled on a reel. The reel diameter is about 3 centimeters here. And in order for this tether to work, we need to bond together these very thin metallic wires, and creating these bonds in a reliable and scalable way is the main technical challenge of building a Coulomb drag device, either e-sail or plasma brake. And currently we have experimented with many methods of creating these bonds. Previously we explored ultrasonic bonding technique, and we explored so-called diffusive welding, diffusing bonding technique. But currently we are using simple mechanical twisting of the wires to create the bonds. And this method relies on plastic deformation of the wires and the friction between the wires. And currently we are using 50 micrometer aluminum wires, but it is in our plans to reduce the thickness first to 32 microns and then as a next step to 25 microns. And currently, so this 50 micrometer wire was selected in our initial study. We are presently using 50 micrometers just to make it easier to handle this wire manually at this stage. So that once we have everything automated, we expect that we can reduce the wire thickness to 25 micrometers. And here is a picture of the current tether factory, what we have, manual tether factory at FMI. So this is a manually operated machine, and it can produce about 1 meter of tether, e-sail tether in quarter hour, in 15 minutes. And we are currently in the process of automating this factory or generating an automated version of this factory. So this version which exists here was made completely by hand by Dr. Petri Toivanen. He designed and built this factory himself, and that is a quite major achievement, I would say. Needed a lot of creativity from his part. And now that it works manually, the next step is to automate it. So that means to add servos and stuff like that, so that it can be automated. Okay, and then we are also flying experiments. So here is we are launching a CubeSat in August, September this year, whose name is S-Cube 2, or not. We are not launching it. It's the University of Tartu in Estonia, which built the CubeSat and is launching it. But we delivered the Coulomb drag experiment on this satellite, and our experiment is seen here in a semi-finished state. So this experiment takes about one unit of volume in the CubeSat. And then what kind of missions one can do with the e-sail? So exemplary missions. So one of the missions that have been studied at some length is the so-called multi-asteroid touring. This was originally proposed by us to ESA in 2016, but it was kind of picked up by ESA for further study, but it was eventually not selected for implementation, which was not a surprise to us because ESA selects only mature high TRL technologies usually for science missions. But anyway, since then, this mission concept has been developed and analyzed further by Jakub Bibski et al. So this is in this concept we fly a fleet of CubeSats, interplanetary CubeSats, for example, a fleet of 50 3-unit CubeSats, each of them using single E-sail tether of 20 kilometer length, and each of them can do a flyby imaging of the main belt of asteroids, about 10 asteroids. About 10 main belt asteroids can be flyby imaged. And then at the end, we return the data to Earth by making an Earth flyby so that the radio linking costs are small here. So we don't need the deep space network at all in principle here. So if we make all these satellites, these spacecraft autonomous so that they can navigate based on the asteroids, this is of course a non-trivial problem. So nobody has done this kind of, at least not in the CubeSat scale, nobody has done this kind of completely autonomous optical navigation yet in the solar system. But anyway, it's in principle doable. And then if one does it, then we don't need the deep space network at all. We just need much smaller antennas which downlink the data during the final Earth flyby of each of these satellites. Okay, and then we have the company that I was talking about in the beginning. Well, I mean not in the seminar, but in the talk before it. So its name is Aura Propulsion Technologies, aurapt.fi. It's a startup company in Finland where I'm an advisor. And they have a mission concept that they called North Star. It would be a multi-tether, sun-powered, solar-powered, about 25 kilogram mission out of the solar system at high speed, 100 kilometer per second speed of that order of magnitude. And it would be based on an inflatable or let's say deployable, better say deployable structure, because it's not necessarily inflatable. It could also use spring forces. So deployable solar collector, which also acts as a parabolic radio dish antenna and also acts as the frame of the E-sail, where on the perimeter of which the reels of the tethers are attached. And because of the solar collector, this could stay functional even up to 30 AU distance without using any radioactive materials on board. So the idea here is to come up with a concept which is a low-cost method of sending a very small payload out of the solar system at high speed. And low cost is enabled by the relatively low launch mass, so 25 kilograms to escape orbit, and no use of any radioactive materials. Of course, we could add radioactive radioisotope battery if we want, and then we could prolong the distance up to which this payload stays functional. Okay, and then we could also use the E-sail for off-Lagrange point solar wind monitoring to prolong the warning time for space weather forecasts. So this requires flying a spacecraft in a non-Keplerian orbit, so it requires constant propulsion, for which one in practice needs a propellantless propulsion system such as the solar sail or E-sail. And then last but not least, we have the plasma brake concept, which is for deorbiting satellites in low Earth orbit. And for this, we have an ongoing ESA project whose name is Dragliner. Okay, so then about some numbers about this fast flying outward from the solar system. So we receive about 0.5 millinewton per kilometer of tether. So for example, if we have 30 tethers, each of which is 20 kilometers long, then we get 0.3 newtons of thrust at 1 AU distance. And this thrust scales as 1/r. And the tether mass per unit length if we assume this 25 micron aluminium, which is our goal. So 5.7 grams per kilometer, and then total tether mass is 3.4 kilograms. I mean, all these 30 tethers together weigh only 3.4 kilograms. And the high voltage power consumption 130 watts in total at 1 AU. And this power consumption scales as 1 over R squared. And if we assume everything else in the system, so reels and high voltage remote units, auxiliary tethers, if they together weigh 7 times more than the main tether itself, then we end up with total mass of 25 kilograms in this case. And in this case, the acceleration would be 12 millimeters per second squared, which is 32 kilometers per second a month. In the initial stage. Of course, this acceleration goes down as we move further from the sun. But anyway, about 100 kilometers per second asymptotically outgoing speed seems to be within reach with these numbers. Here is another calculation which I did it back in 2010, but it's still relevant. So that was a calculation using slightly different assumptions for the different subsystems of the e-sail. But anyway, so there the idea was how to send a 100 kilogram payload out of the solar system. So then the result was that for 100 kilogram payload, we can achieve 75 kilometers per second outgoing speed, which means that in about 13 years, we reach 200 AU distance. So in that case, that was some kind of that was a goal, how to reach. It came from somewhere, I don't remember where, how to reach 200 AU distance in the minimum amount of time. So if we have 100 kilogram payload, then we can do it in 13 years. And then if we have like margin, so if we want, for example, 50% payload margin, then we can do it in 14.7 years. So and 66 kilometers per second. So in this case, adding this payload mass doesn't, I mean, it slows down the mission, but not very dramatically, which is kind of good. And even with 500 kilogram payload, we still get it to 200 AU in 25 years, which is also interesting. Okay, so then I will discuss about the plasma brake. So that is the ionospheric application. So plasma brake is negative polarity Coulomb drag sail in low Earth orbit for deorbiting satellites and upper stages also. And in this case, the maximum tether length is, so we use a single tether first of all, and the single tether is, we deploy and stabilize it by the gravity gradient, or Earth's gravity gradient in this case. So we don't spin using the centrifugal force, but we use the gravity gradient of the Earth. And the maximum tether length is about 5 kilometers. This is limited by material conductivity and tensile strength. Here is a particle in cell simulation of the plasma brake. So now the stream arrives from the right. So on the left hand side we have electrons. So there is a vacuum of electrons, complete vacuum, absence of electrons around the negatively biased tether, of course, because electrons cannot approach this negatively biased tether at a close distance, and then this negatively biased tether attracts ions. So ions make close passes, flybys of the tether, and these flybys scatter these incoming ions, and that produces the propulsive effect in the negative wire case, negative tether case. There is also a thrust formula for the plasma brake. Here is the approximate thrust formula. This is calibrated by those simulations, and this formula is surprising. It's a remarkably accurate representation of the particle of the peak simulation results. And numerically 87, I mean, typically in low Earth orbit in ionosphere, 87 nanonewtons per meter. So this is about 6 times less than in the E-sail, in the solar wind. And then here in this plot, we have this mass of the, I mean, how much mass we could deorbit by this method. So we can have, for example, 300 kilogram satellite at 700 kilometer initial orbit, and then we could deorbit it by this method in about 1 year. And then if the orbit is much higher, if it's 1,000 kilometers, for example, and 100 kilograms, then it takes almost 2 years to deorbit it, and so on. And then what is plasma brake's power consumption? So again, the OML theory for ion current collection, we need that. Now there is one additional factor, which I call chi, in front of the expression, which models the emission of secondary electrons from the surface of the wire. So when a positive ion hits the negative metal surface, there is a potential for it to generate a secondary electron. And if so, then this secondary electron increases the current collection, effectively increases the current collection of the tether in this case. So the power consumption is about 0.2 milliwatts per meter, and power per thrust is about 2 kilowatts per newton. Sorry, I mean 2 kilowatts per newton. There is some typo here. So this is about 2 times larger than in the solar wind case, and this is about 10 times less than for Hall thrusters, which typically have 20 kilowatts per newton. Then one important aspect of the plasma brake tether is that it is so thin, it is safe to other space assets. So this 5 kilometer long plasma brake tether, it is so long that it has a finite probability of colliding with an either active satellite or debris satellite. Or at least this is so if we don't do anything to prevent such collisions. I mean, we could also actively try to avoid those collisions by controlling the voltage of the tether actively. But if we don't do that, if we just fly it blindly without caring about collisions, then it's about, very roughly speaking, 1% probability per year that such collision occurs. But such collision is not, it shouldn't be harmful for the satellite because it only makes a linear 0.1 millimeter scratch to the satellite surface. And these kind of scratches of this depth occur all the time in all satellites by the natural micrometeoroids and existing orbital debris. And for this reason, we consider the plasma brake tether essentially safe to other space assets. Except in the case that if 2 plasma brake tethers collide, so then both are severed. But that starts to be a concern only if there are of the order of 10,000 plasma brakes in orbit simultaneously. So we are not quite there yet. So, but this is something to keep in mind also. Okay, so then here is some kind of brief history of the Coulomb projects and events. I think that my time is starting to be out soon, so that I will not go into details of this, but just notice this E-sail was invented in 2006, then the plasma brake 4 years later as a spin-off of that, and then we had one EU project where we demonstrated demonstrated production of even 1 kilometer long tether by ultrasonic bonding. Then we had one ESA project, asteroid touring by electric sail technology. Then we had ESA CleanSat project, where we created the GRL3 level 3 prototype of a plasma brake module. Then Aurora Propulsion Technologies was founded in 2018. And then currently we are running ESA Dragliner project for further development of the plasma brake. And then now we are launching these two CubeSats, S-Cube 2 and ForeSail 1 Prime this year and next year. There have also in the world, there have also been other studies and related activities, and some of them I am aware of, and probably many of them I'm not aware of. So anyway, one activity happened at NASA Marshall Space Flight Center, and they are actually now intending, I just heard last week that they are actually trying to restart this activity, restart the ESAIL activities in the plasma at Marshall Space Flight Center. So in this first project, they did a plasma laboratory experiment trying to measure the ESAIL effect in a plasma chamber. And then Pisa University has written lots of papers on ESAIL trajectory optimization. Then there have been some control algorithm studies in China. Several papers have come out from them, and then we have the Tartu University Student Satellite Program, which has been an active partner for us flying our test payloads. And nowadays this ForeSail, which is a Finnish Center of Excellence of Research of Sustainable Space, so we are part of that, and that funds our ForeSail series satellites, ForeSail 1 Prime, and then ForeSail 2 and 3 in the future, hopefully. Okay, so here is my summary, Coulomb summary. So single tether ESAIL for interplanetary CubeSats, the multi-tether ESAIL for larger spacecraft for higher amount of thrust. The ESAIL thrust decays slowly, only as 1/r. The plasma brake exists to deorbit any, I would say it covers the entire space of D4D satellites and upper stages using a few kilogram package. D4D means designed for demise. So it means a satellite or upper stage which is designed in such a way that it burns completely in the atmosphere during re-entry. And in that way, it's safe to people on ground, so that there is no risk that anything falls down to ground from D4D satellites. And the majority of satellites will be D4D in the future because if it's not D4D, then it needs a targeted re-entry in order to be safe, and that can only use chemical propulsion. So non-D4D satellites will become probably more rare because they are expensive, or otherwise they are not safe to people on ground in the long run. So the plasma brake in that sense is a relatively complete solution for the orbital debris problem in low Earth orbit. Not fully complete, of course, but it addresses a large fraction of the significant fraction of the future satellite population. And then plasma brake microtether is safe to other orbital assets, except to other plasma brakes. Okay, so this was the end of my presentation. And I'm ready to answer your questions at this point.
Yeah, Pekka, so thank you so much. You describe almost everything in the universe now. But let me ask maybe Ian. Ian, you're the moderator. You go ahead first. I would later on ask questions. So anyone has questions, please write it down in the chat box, or just ask or raise your hand. Okay, Lainey, go ahead.
Yeah, just a simple question. So how did you deploy your world in the space?
Yes, so we use centrifugal deployment. So we spin the satellite, and then the tether has a small end mass, and then the centrifugal force pulls out the tether from the reel. But the reel we use is also motorized. So we turn the reel active by an electric motor, and then in addition to that, there is a small tension of the tether created by the centrifugal force. This is the method that we have used thus far. So, but we could also think of dropping the motor in the future and just using some controllable brake of the reel, and just let the centrifugal force pull the tether, rotate the reel. So this is a technical question, either motorized or not.
I see that you have a very long tether, in your design. How heavy it is?
I mean, it's not heavy, so because it's so thin. So I had the number in the presentation somewhere.
Kilogram or 10 kilogram?
No. It is much less. So it's
Is that right?
we are talking about grams. So here, if we have 30 tethers, each of which is 20 kilometers long, so that means 600 kilometers altogether of tether. Then the total weight is 3.4 kilograms. So this is
okay.
It's very thin tether, very low weight. But this was assuming 25 micron aluminium, which is 2 times thinner than the one that we are currently using. But we are confident that we can use this 25 micron aluminium once we have automated the tether factory. So therefore, I kind of dare to base these mass estimates on 25 micron aluminium.
Well, of course, this is not the place to discuss, but I think that I would be very interested in having some cooperation, between I mean, using some cooperative program between Finland and Taiwan.
Okay, yeah. Let's discuss that by email separately. Yes.
Yes, certainly. Yeah. And I think ESA would be happy to do that. I mean, ESA Kallio, not the European Space Agency.
ESA Kallio.
Okay, good. Yeah, right. In fact, I asked him to introduce me to you. Anyone have questions to Professor Janhunen? I think this is a very interesting talk, and I would say almost a very ingenious idea. Yeah, if I can say that. That's why we would like very much to work together with him and to learn from him. This is a good opportunity. Anyone have further questions? Monza, do you have questions?
No, I think I need to learn more for this.
You're supposed to work on this problem, right? Remember. Okay, I think that one of the things that I think that the Professor Janhunen, he started by actually he was a I would say a theoretician, right? You first start by doing simulations.
Yes.
And I was so surprised to see that this solar interaction model could be turned into this solar cell idea. There was really a breakthrough and a wonderful idea, wonderful change. And there's also the students here should learn from from you, basically.
Yes, I think one can at least learn from that basic research. That it's beneficial to do basic research because it can lead, it may lead to some spin-off inventions that you don't see at first. So just by studying, making basic research of the study of solar wind interacting with planetary magnetospheres, in this case, yielded a completely new propulsion method for space travel. So this is it was definitely not planned when I mean we were studying the auroras and magnetospheric physics, which was not supposed to have this kind of technical applications.
Mm. Now, Pekka, last question I ask you. When you have this idea, when this solar cell e-cell idea, it was in the summer or in the winter?
It was winter, actually. It was winter.
Winter, because you cannot because it's all dark, right? You cannot go outside. You just have to stay home and think.
Yes, but on the other hand, I must say that I got this idea also from spiders. So because there are spiders that deploy like single wire,
the net, right?
And then they let the wind carry them. So the wind carries the spiders in summertime in Finland.
Okay, also summertime.
In the summertime, we have some species of spiders. I mean, they move from place to place by using the wind. So they deploy this very thin thread that spiders can produce, and then the wind.
Wow. Okay, I understand. Yeah. Right. Great.
They can travel from place to place by using that method, and this was actually one of the things in my mind when developing this concept. So
that's interesting.
So although it happened in wintertime, also summerly activities were part of the equation, so to say.
Yes. So this is a secret, right? Secret of success. The secret success that for young people here listening is that you have to be how to say, but pay attention to many things, and then be and then they come into use. Sometimes very useful. Yeah. And the connecting spider to solar system exploration is fantastic. Okay, Pekka, I hope that in near future we could invite you to visit Taiwan. Have you ever been to Taiwan?
No, I haven't. No, but
is it too warm for you? I hope it's not too warm for you.
Sorry, what?
I said I hope Taiwan is not too warm for you.
Yeah, I don't. Well, I don't know how to. I have to check how to fly there, because I mean currently we can't fly over Russia, so therefore the distance is long.
No problem. We could.
Yeah, so
you could go south first. You could go south first. Yeah. Okay, good. Pekka, thank you so much. And we will keep in touch by email, or by other means. And thank you so much to Fano to get into touch with you.
Yes.
And then we hope that we could develop some cooperative projects. Yeah.
Yes. I'm looking forward to that. Yes.
Yeah. Okay. Thank you. Thank you so much for everybody. Yeah.